I successfully plugged in the HDMI cable today. It's the first time in like 3 weeks that I failed to pull up Twitch to make sure that this is all rocking and rolling. All right, I think we are good. So today is March 19th, 2025 here at ASU, CSE598, Advanced Software Exploitation. And we're kind of having a do-over here, right? Yeah, we're going to talk about Windows. So the only meme that was posted is a fair dunk. For those that are not aware, this is, I think, the second, might be the third time. I've tried to make Windows easier on the dojo, and it is always right around this time in spring break. And so my spring break consists of me building a Docker container. I've gotten very good at building Docker containers. Last year, it took me about, for a little bit of context, about 2 hours to build this Docker container and see the impact of my changes, which is great when you're not entirely sure if things are going to work or not. Now I've managed to improve that now. It's up to like a 20 minute feedback loop. Drastic improvement. Made an awesome spring break for me. And hopefully you get to see the results here. So this was our plan. We were going to do Windows kind of leading into spring break. We had class, and then I tried to demo some stuff, and then it all caught fire, and I did some hidden stuff. For the record, it all did work like the day after, but I didn't think it was fair to literally assign something going into spring break, so we just kind of didn't do that. But it did all work. All right. I did fix it before spring break. Then we had spring break and we did kind of nothing. So what's happening? Well, we just kind of, yeah, whatever. This was the Windows pain. That's what we get them. So we'll do what we were going to do leading into spring break, starting right now. You'll note that right now, this is no longer going Friday over. I'm putting it on Wednesday to Wednesday. We'll see what happens, right? This is if I can catch back up on the plans of what we're doing, I think I'll be able to do it where this Windows stuff launches on Friday. We'll see. But right now, I'm really only saying, hey, we'll go Wednesday to Wednesday. Cool. So what is the result of these efforts here that are invisible to you? That is a lie. I was going to do that right now. I'm going to do it right after class. So it's not listed under the course, but it is live. There's much less clunkiness. So like if you started Windows before, there was like this, hey, you shut down Windows wrong, like that's gone. There were links that didn't quite open up things. There were tools that were kind of hidden. That's all been squared away, and that all works as one would expect. So there's a lot less clunkiness in your tools. You do still have to right now start Windows manually. That is something I can fix, but that one has a couple hour feedback for me to push things. I'll try and get to that one. After class, there will be one new challenge. The challenge exists. I've verified it. It's tested. It's automated. It works. It's cool. Hopefully.
Is it the middle of the content challenge or the end of the content challenge?
End. So it's actually a new concept, right? So this kind of Windows crash course stuff is meant to be the equivalent of like CSE466's memory corruption, right? Kind of that tier of concept, except we're specifically pointing out things that are different in Windows, right? So it doesn't make sense for me to be like, oh, did you know that you could use printf for like a no terminator to leak something on the stack? Yeah, you can do the same thing. Like that clearly exists in both worlds, right? And if we were in Mac OS, that same type of thing would exist. I don't think there's anything interesting in duplicating stuff that hopefully you can rationally say, yeah, this concept still exists. Instead, each of these challenges try and point out something that is something you're familiar with, but that is specifically different in Windows. The existing challenges, if we take a look here. They start off with just first a sanity check. Then they go into just a basic buffer overflow like memory corruption. Then they say, hey, here's ASLR because ASLR works a little bit different. Then we say, hey, well, how do dynamically linked libraries? How does that impact ASLR? Because that is also something that's slightly, again, different than what you've seen in Linux. Then these next 5 through 7, which I'll try and rename it while I'm at it. These are all shell coding. So it's do something pretty relatively simple in shell coding, do something a little bit more advanced with shell coding. And then level 7, what you end up doing with shell code is something that you just haven't done on the Linux side. And so it's meant to be kind of a gradual pace. There are videos about this, but like level 7 here, the idea is you have to navigate a struct called the teb and the peb to figure out where your library is in memory, which is something that you just don't have to do on the Linux side. Like this concept doesn't exist of navigating a struct in userland to figure out where something is in memory. We can take a look at that today if we have time. The next 3 challenges that are slated, but the only one will for sure go live because it's been adequately tested, is taking a look at stat canaries and how those are different, which I have a demo where we can talk about that a little bit as far as how the stat canary works. But there's 3 levels I have planned that are applications of the stat canary on Windows. And then I have additional levels planned as well. Friday is going to be a fun day. That to build on the stat canary and then go into rock. And then my stretch goal here for Friday is doing something with CFI and or shadow stack if the shadow stack works. On the VM, I haven't tested that. And so that'll round out at anywhere from 10 to 15 levels. But you're getting 3 for sure. 3 I can give you. The rest we'll see. We'll see what happens. So the idea again is to just kind of see existing concepts that you hopefully have some idea of how they work and kind of reason about what's different in Windows. The follow-up module is totally different. It's kind of a pivot in a different direction where we probably will not be writing a lot of assembly. We'll be writing mostly C, C++. But yeah, so there you are going to get to see some fruits of my efforts there over spring break, although I will confess that I did try and take a break myself as well. So plans. I talked to people beforehand. Nobody did anything over spring break, which was the assignment. So you did good. We'll take a look at the calling conventions in practice, right? I said, does anyone remember what the calling convention order is on Windows? It'd be a stretch goal if it happened to stick. You didn't use it, you didn't know. That's fine. It's different. We know it's different.
That's all we
okay. That's good enough, right? That's all I know a lot of times. Is hey man, something's a little bit different. Do you know how to find it?
MSDN though.
Okay, MSDN. Right, that is MSDN is the equivalent of our man page here, and so the convention that they use, we'll see if this has it, is fast call. But rather than read the docs, let's actually take a look at it. So I'll start fresh. We'll blow away any work that I had to practice. Boom. All right. So we'll start fresh here. Well, Windows Start, Windows Connect. I also learned a bunch about PowerShell.
How is it different from command?
It's very different. So it doesn't make sense for this course. So it's not something I'm prioritizing, but I think it would be fun to make a learn PowerShell like module and throw it in there. It doesn't make sense. It could make sense for this course, but in the current iteration, it doesn't. I should not have restarted that instance. Come on.
Does take a minute.
This could just be me misremembering things because my dev setup is now pretty sweet. A year plus of Windows pain do that to you. So we mash that, but it's good to see it live on prod. A minute, man. You are not kidding. Okay. So to your immediate question, what is different about PowerShell? PowerShell is, and this is true for Windows as a whole. Windows design, when we think about Windows versus Linux, Linux being open source, a lot of things are just kind of siloed subsystems, and they don't communicate with each other, right? Windows is very, very, very heavily object oriented. There's going to be pre-recorded lecture videos for the Windows 2 that shows this a bit more, but if we were to summarize Linux, we say everything is a file, right? That's like Linux exposes things through the file system. And we use that trick to kind of get around a bunch of things. With Windows, everything is an object. And this exists in your high level, like C Sharp, right? Very object-oriented Java-esque language that exists kind of in your middleware. When I say middleware, I'm referring to like .NET. And it exists in the kernel. So one of the things that I said last week or 2 weeks ago was that we have the equivalent of open. You call open on Linux, you get a file descriptor, right? It's just this number into a table. When you call create file on Windows, you get a handle. Like, okay, it's still just a number we were to look at, right? But the internal representation of this is a lot more complicated and a lot more structured. And this is pervasive through almost everything in Windows. And it shows in PowerShell. So I type ls. ls isn't real. This isn't even like a command. This is a convenience thing for us Linux people to be like, oh, maybe I know how to use this thing. Everything in PowerShell is called a commandlet. They are very structured. So like when we think about Linux, there's all these like weird kind of ha-ha, he-he mnemonics. We have to know the binary less. We have to know grep. We have to know, right? There's like these cat, right? That's all craziness, right? That's all crazy talk, right? For the open source people that want to be funny. Windows is structured. It's for more civilized people. And so everything in PowerShell is a commandlet that consists of a verb followed by a noun. So what's actually happening when you type ls is you're calling get child item, and I happen to be on my file system. Yeah, okay, yeah, that's cool, Robert, right? You just typed something different, got the same output. But it truly is object-oriented. What do I mean when I say that? So GM is shorthand for get member. I'm running the get child, which is the same thing as ls, and we're going to pipe that into get member. Well, this is going to show me all the properties of these objects. And so these are actually file info objects. And these are all of the methods and properties that exist for that object type. And so what I see up here is just like a preview, a shorthand of what is everything that is in this object. If I want to see everything, we select object star, and then let's format it. Let's grab just the first one. You can't see this. I'm typing dash first one. And then I want to format this as a list. Right? And so these are all of the properties for the first file that I have here. But you're like, okay, but in PowerShell, this abstraction of like a child item isn't specific to the file system. I just happen to be in the file system right now. I can cd into my environment. My prompt of my terminal in PowerShell is not in my environment. And if I were to type get child item, you know what I get? I get all my environment variables, right? But it's not just file system in my environment. All of these things are called PowerShell drives. And so right now, and this is an extensible system, these are all of the drives that are available. A lot of them are file systems, but I could cd into my registry, right? And modify my registry by using this like get child item, create child item, or new child item, this type of abstraction. And everything is abstracted into an object. So all of my commands have a noun and a verb. And they're very like structured as far as what are they? They're predefined. These are the verbs that exist. It is extensible. You can add more verbs. And you can also say, this is get command, GCM, and I'm typing -no or -noun. I can say, show me everything that I can do to an item. Well, here's all of those commands. They do have the equivalent of a man page. The get help, or the shorthand is just help. And they are pretty good. There's several different versions of PowerShell. You want to be on like PowerShell, I think 7 or later is kind of where things standardize. Then we get something that looks like a reasonable man page. And then one of the cool things about their man pages, if we get to the bottom here, is you can, where it says remarks, you can specifically request for examples or full detailed documentation of literally everything there. It's actually a pretty cool system. But it takes a bit to wrap your head around what you're doing because you no longer grep for things. Instead, everything is an object and you call functions on these objects that generate more objects. And so if you were wanted to like get process and then export to a CSV named procs, let's put that. Can I write there? Maybe. That is going to automatically deal with the data conversion of the object, and then I could import them back in. And I have all of that same data, right? And so it's doing the lifting, the abstraction when you have something inside PowerShell is almost always an object. Even if you just have something as simple as a string, it's actually an object of a string that you can then call things and extract upon. And this all ties into .NET, which is that kind of standard communication layer that wraps the Win32 API. So when we talk about like create file, it gives you a handle to a file. When we look at this file info that I have here in PowerShell, the file info is an abstraction over the .NET file, which is an abstraction of the Win32 file, which is the object that the handle points to. And you find this consistency across the entire stack, which is cool. All right. So let's make something now. We'll endim example .c. I'm going to include windows.h, and let's include standard IO. So the only thing we remember so far is that there are different calling conventions. And that's true. But to really see the kind of the what's different here, I need 5 or 6 arguments. And we'll take a look at this in the debugger. We'll have some call me function. Let's have we're just going to sum these. Total is 0. Total plus equals, or total equals arg1, arg2, arg3, arg4, arg6, and we'll return total. All right, that seems reasonable, right? Okay, I'm going to invoke the super secret dev enter magic. Remember, by default, you can't run the compiler on the terminal. That needs to get added to your path and some environment variable set so that the compiler works. I should just add this as a default thing, but then it'll break somebody's setup. So I'm going to call the compiler on the command line. The MSVC compiler CL/GS says I want to enable security stuff. I want example.c. I want to link it. I want, I think it's VA high entropy. All of your binaries have this setting. The high entropy is ASLR. So ASLR without high entropy actually randomizes less bytes. You guys are dealing with the hard ASLR in this module, which, ZI. We want, ZI gives us our debug information. Does anyone remember how debug information exists on here?
There's another file.
There's another file. It's a .pdb file. So I have my executable, and then I have the PDB. Got to have both of these right next to each other, otherwise you're going to have a bad time. One of the things, fun fact, that you can do now, you can get a proper debugger in the terminal like a rational person. It's CDB. It's the underlying thing that sits underneath WinDBG. Oh, yeah. I'm over hitting it on my keyboard because on my dev setup, I can. Okay. So hopefully you notice that these now actually work. So we actually have x64 debug, which is nice. That is a competing debugger that many people use. I'm not going to show it today. It's worth checking out if you're interested. All right. So let's take a look at this example binary in the debugger. I'm going to add a shortcut so that you can get to this on the left-hand side. It is on the short list. However many times you've done this, I've probably done it like 20 times more. Okay. So I am in this binary. One of the first things you want to do, lm, list module. This is showing me it's similar to VM map. It's not the exact same thing. These are modules that are getting mapped in, and we get to see whether we have symbols. So we see here that we did pick up the private DB or PDB symbols for the example binary. I'm contemplating giving you guys one of these without the PDB symbols on the tail end. I'm just going to tell you right now that things are way, 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 way harder without it. It becomes a very big mess. I'm not going to do it to you a lot because it is just time-consuming pain of hopping around and figuring out where you are and things. But I think I might do that in the last level. So we set a breakpoint with BU. I want to break at main. Now, the correct thing to do is to specify the module followed by the function. So I want to break at example main, because there could in fact be more than one. I can list my breakpoints with BL. I hit G to go. We're going to go until we hit main. All right, we hit our breakpoint here at main. If I want to unassemble the function, I can type UF. Now we could UF main, but I can also UF, and then what I have here is an at symbol. So in GDB, we use $sign to prefix registers. In WinDBG, we use an at symbol. So at rip, I'm saying unassemble the function that is at rip. And you'll see that if I evaluate like what is rip, so question mark space rip, rip is at 7180. And we happen to be at the beginning of the function, right? But if I were to step just a little bit further, and I run this again, examine the function at rip, and then let's evaluate rip again. We see what we see here is that despite the fact that rip is no longer pointing to the beginning of the function, when I did unassemble function at rip, it is still unassembling the entire function that I happen to be, right? Because it has that context. It's looking up for the symbol and looking down for the rect. And so we get this context. Now, I did skip past what I was really looking for here, but we can see a little bit of what's going on here. Like, we've seen calling conventions before. And we saw my function here was just arg1 is 1, 2, 3, 4, 5, 6. And what do we see here? So you probably, maybe, if you remember everything that I said 2 weeks ago, it didn't sound very important then. You probably remember EC or RCX, RDX, R8, R9, right? Those are the registers that are used for the first 4 arguments. And then I said, well, the registers after there, the arguments after that get pushed to the stack. That was kind of true.
It's not true.
Well, is it? Is that getting pushed to the stack?
This can move to RSP plus 1.
Yeah, it's getting moved to RSP plus 20.
Somewhere in the step.
Well, yeah, it's going on the stack.
But not directly.
But it's not
on the step.
literally getting pushed, right? Well, why X20?
Something before X20.
Wait, what's before X20? Right, this is a weird thing, right? So the answer here is with fast call, which is the convention that you'll pretty much always see up here in userland. There is a shadow space that is made on the stack as if these first 4 values were pushed onto the stack. Imagine the first arguments were on the stack. This would be at RSP, RSP plus 8, RSP plus 16, RSP plus 24, and then we get to RSP plus 32 here, right? Now, we aren't actually putting them there, right? But we make the space as if we did. This sounds weird. It sounds unnecessary. That sounds like a waste of time. Why would anyone do this? Well, there's a couple reasons that that this happens. The first is, what if this function needs to use these registers for whatever reason? Well, wouldn't it be nice if we had a standard place to put them? That'd be kind of nice, wouldn't it? Well, that's what this space on the stack is there for. So if this function needs to use these registers, it has the space predetermined ahead of time for where to place them, where to store them. Additionally, when you're looking at a call stack, right, I showed you K. We're like, oh, this is kind of like mmap. What we see is, and this is a weird thing to read. Hopefully we have time to take a look at it. Is the child stack pointer in the same return address for the call stack. But if you KB, we get this output. This is showing me, it's the same data, right? It's the call stack, but it's now showing me the arguments to the child. Because you can utilize this convention such that, imagine that we had some kind of explosion, right? With several calls beat. And I'm like, how the heck did I get there? Well, you can, with a compiler flag, force these args to be filled. The effect of that is when we get our stack trace, we can look at the stack to understand the arguments that were passed to each function. So that makes it easier to debug.
Almost.
Okay. So you don't see it here, which is a bummer. I'd have to find the compiler flag. This would be our CX. This would be what's in our DX. This is what would be in our 8. This is what would be in our 9, right? If I forced it to fill it. Because what would happen is up here, it would use those spaces. It would fill it regardless. It would just, we're putting the values there as well. If the values were there as well, then this shows me the arguments to the function. So when I'm looking at this call stack, not only do I get to see thread start, it had a func called main, which called invoke main, which called main, which called example, or call me, or whatever I called it, right? But I would be able to look at the call stack and say, well, main was called with these arguments. Example me was called with these arguments, right? And I don't have to worry about the registers, like what's in our CX, doesn't matter, because we stored the arguments that were being passed to the function call on the stack.
But that would only show RCX, RDX, R8, and R9. Or just the 4 arguments.
For
Not anymore.
For this view, it is showing me the 4, but there's nothing stopping me from examining the stack directly, right? At which point, if there were 20 arguments, then I could see all of them and I would know exactly what the parameters were that were passed. So it makes debugging easier because you can read the call stack as a history of not only what functions were called, but what were the parameters that were passed to each function to get me there, right? If I were trying to do the same thing in GDB, I run into this problem of, well, I don't know what was in this register 3 calls ago, right? I need to hop to that information's gone. And so if we were to force these to be filled, that gives me, which is a debugging trick, that would give me an insight into the entire history of how I got from A to B, from the beginning of the process on. All right, now I skipped the example, so we're going to have to restart. Now I want to break on call me. So break on call me. We'll go. I am in main. We'll keep going. Let's unassemble the function it then. All right. Wait, what do we see going on here? When I'm inside this function, what is it doing? ACX is going to, this is weird, right? Because this is before I'm subtracting RSP. When we think about the prologue, right? On Linux, what does our prologue look like?
You subtract that.
RSP. No, we say we push the RBP and
Okay.
we push the RBP.
We have saved RBP. But yeah, no, it's kind of there.
Seen it a million times ago.
Right? Yeah. So we do the push, we do the push RBP, we subtract RSP, then we throw a canary in there if we need to, right? Well, up here, the first thing this function is doing is exactly what I just described, right? It's saying, hey, I might need these registers. And you'll note that these are 64-byte slots, or not 64 bytes, 64-bit. 64-bit slots, so they're 8 bytes, but it is not zeroing out the higher order parts of the stack, right? So this is treating RSP plus 8. Why plus 8? I said it was RSP, right? Because it was supposed to be, if we scroll up a bit here, boop, RSP plus 8, RSP plus 10, RSP plus 16, RSP plus 20. Why is it different now? This isn't a trick question, and this is something you should know. Yeah, just thinking about what happened. What happened between when I did this and I went into example? What I said is true. But why does the assembly look like? We talked about prologue.
Is it saving the register state of the previous function?
So what is at RSP at this point? Before I started executing call?
5 or the fifth argument.
At literally RSP?
No, RSP plus 20. Oh, you meant at the RSP?
All right. So hopefully hopefully RSP is 7130 here, and I didn't go good. If I do, what do I want? Give me the quad word at RSP, and I only want 1. What is this going to be?
Should be RCX. What was it RCX?
It's a saved return address. We just did call. What does call do? Call pushes the saved return address. And so if I were to double click on this guy, we scroll up a little bit, we'll see that that is the address that's just after call, because the act of calling pushes the saved return address. That's why up here it would be RSP plus 0, RSP plus 8, RSP plus 16, RSP plus 24, right? But since we did this call, there's now the saved return address there. And so what up above was RSP plus 0 is now RSP plus 8, because we have to get to the other side of the saved return address to start filling in those slots, right? And so we're going to load in those values. Again, they are not filling the whole quad word if they don't need it. This will not zero out the upper half, because this isn't a register, this is a memory location. And this can make reasoning about what are in these memory locations, and you start talking about like what is in argument 5, very weird, because you have to know the size of the argument. So like right now, we haven't done this yet. So let's see what's in RSP plus 20. That one's easy.
What's ahead?
So if I do dump quad words at RSP plus x20, I could also do 20h, it would be equivalent. This is going to dump out the default number of keywords. So it's going to just give me more, right? And I generally speaking do this, but if I want to specify how many I want, you do L and then the number. So I do L1, I can do L100 if I wanted more, right? I'm just specifying how many I want. I'm going to try and keep it limited and use as much functionality as I can, just so that you see it. So the value that's in there right now, before we do anything, is, and we can see that unassemble at rip, limit 1, right? We're going to do this right here. And so it was here, we're going to move whatever was in the lower half of R9. T for trace. Okay, now, oh, what happened? Where did we go? Let's unassemble the function at rip, and let's evaluate rip. I hit T for trace, which should be the equivalent of like a step, but the debugger just was like, yo, all of this stuff is kind of the same thing, right? You don't want to hit T 4 times, do you? So pay attention to that because the debugger it decides what's important, right? Where you want to go. So now we've done these other things. Let's take a quick look here. Let's dump out some quad words. I would want RSP plus 18, and I want to print 4. This should be printing out these 4 values that were just placed onto the stack. Hopefully one of them is funky. That does look a little funky, right? It turns out memory locations used to have some kind of pointer in it, right? And since we only wrote a D word, it's this 1, 2, 3. Did I go too far? Whatever. But you see it here with the 1, 2, 3, right? That the higher upper half of that memory location still has its old value. So if I were trying to debug and reason about what this argument is this argument 7FF61?
You don't know.
Maybe. maybe not, right? We would have to actually, it's great that it's there, right? For us to reference, but we have to understand what the function is actually doing with the data, because the compiler is not going to spend time zeroing out memory that it doesn't care about. And this is not only for D words and Q words, you can and will see byte. So
How do you know how much of it was the argument?
Well,
I think you'll have to look at this.
what happened here with this function here? How much of it actually mattered? Right, it's just a D word. So I have to know that I only care about a D word of that. It's a great question, but that's why we're looking at it right now, because you'll see this and just be like, what? While you're looking at this in the debugger, especially when you're trying to write your own shellcode and trying to do your own function calls here. So we didn't need to fill this space ahead of time, but we do need to make this space available for the call E to use if it chooses. Some call E functions will use it. Some call E functions will not use it. It is up to the implementation of that function, how the compiler decides to deal with it. So we may create this space and it's just unused. Who cares? Where we're just blowing every function call hex 20 bytes on the stack, minimum every time. Okay, so we utilize that space, and then we create our stack frame here, right? We were creating our space for the stack frame. This is why when people ask, like, where's the beginning of the stack frame in 466, 365, it's like a trick question, right? You'll also notice there's something else that's different here when we think about stack frames. What was the first thing that you guys said happens in Linux?
Push RBP.
Push RBP. RBP is looking a little rough here, isn't it? All right. This is powerful shell, says Twitch. Yeah, PowerShell is pretty cool. It's got a steep learning. So you can do the same thing in Linux, right? But we don't enable that flag, at least on our challenges. Windows doesn't use it by default. You have to enable the use of RBP, right? And so in an effort to give you more default behavior, right, something you're more likely to see, there's no, RBP is just a general purpose register. If you do write code for Windows, And for debugging purposes, RBP is useful. The reason RBP is useful is the call stack. So where am I again? Where's RIP? Okay, so we've done the sub 18, right? Once we've done something like that, okay, now that one's still coming back clean. Dang, not doing what I was. But what can happen without RBP is, remember, saved RBP points to RBP, which gives you a nice clean way of viewing stack frames. If RSP gets shifted in a strange way, you can blow up this entire call stack because we don't have that consistent reference of RBP to RBP. Instead, you're banking on values that aren't consistent, right? And so depending on where you are in execution, the backtrace can just be utter garbage and make no sense, and it can have a whole bunch of things that just don't add up if you print it out at the wrong point in time. So if you do that and you're just like, none of these add up and make any sense and go anywhere, it's probably because RSP is shifting, so now the call stack doesn't make sense. Or you corrupted something, right? You could definitely do that. All right, we are at the hour mark. You guys want to call it here for a break, or you want to keep marching? All right, I'm going to take that as a break. Boom. We had a nice little aside where I failed to show, but at least described the concept of alternate data streams. There was the kind of starting question that led to, which is super cool if you look it up yourself. But the probing question was, how do I run the challenge? Because if we were to get PS Drive, we see that there's many file systems on here. There's actually many challenges. What do I need to run? Well, if you look at Z, Z is your home hacker Linux file system. Things may or may not run there, but that's definitely not where the challenge is. The challenge is located, I think it's on what, Y? I remember right? Yeah. There's a copy of the challenge here on Y. You have very good odds. This is like literally just run the binary smoke test. That if I run this, it's going to say invalid process, can't connect. This Y drives implementation detail. Don't try and exploit that binary. Instead, there's a copy of it located at C challenge. That is the binary that you want to exploit. They are, in fact, the same size if you look at them. So why does one work and one doesn't? Alternate data streams is the answer. And just to show that this one does work, there you go. Because the one on the C drive has magic, it's not magic, is signed in such a way that the flag service can verify it. And you can only access that signature from the C file system, not from the Y file system. All right. So we were looking at calling conventions here, and we saw this weirdness. And we saw we are at sub RSP hex 18. Let's make a stack frame. Any reasoning about what's going on over here? We see 0 to RSP. Why?
Totally equals 0.
Yeah, totally equals 0. Right, that one isn't anything crazy. That's just a local variable that happens to be there, right? And so it's hanging out there at 0. But what's going on with hex? We got again hex 20 and hex 28. What are we doing here?
We're moving the parameters back into register. Oh no, I made some.
So ECX was the first argument of call me, but call me is going to call printf, right? No, it's not. I have no idea why it's doing that then.
Because it tracked the RSP already, so it's just shifted the offset to access the variables.
So it did this for the 0, but it's got the stack space here. It doesn't call anything. Like I would have expected it to do this if it was calling something.
Just adding stuff.
Because what it's doing is it's setting up what would be a 5th and 6th argument if it were to call something. But it doesn't call something. So we'll just go with it. And then we add this up. But you see how you get like this weird shuffling around of things on the stack, and this scratch space that is seemingly useless and probably could be optimized a little bit harder, does actually get used, right? And you'll see this in more real functions or functions that do actually do something quite regularly, where there's a lot of shuffling stuff around to fill out that scratch space, that hex 20 bytes, and move things around before we run. Almost always, this one here is not, which is why it's a little bit weird. When we sub for the current stack frame, if this function called something, let's do that. Let's just show it. Showing is better. Let's call print.
Use the info in the code
I'm sorry?
as in the print F line.
Oh, yeah. Good call. We should probably print the actual thing we want. Link warning. VA high entropy is ignoring. Whatever. Not the point of today. All right, so now all I did was I added a printf call. We'll break on example. We'll go forward. We'll unassemble example. If you can type the word example. Okay, this is a, oh, it's not example, it's call me. Let's unassemble the correct function. Okay. Now if we look at the stack, before it was hex 18, now it's hex 38. You will almost always, unless it's a leaf function, see the stack frame grow by hex 20 plus the local variables. Why? Because if the function knows it's going to call something, instead of growing the stack twice, we just allocate the space for those hex 20 for that shadow space for what we know we're going to call ahead of time at the beginning of the function. Okay? So the fact that we were calling printf made this grow so that we know we have shadow space for printf. Any questions about the calling conventions there? Good? Cool. Look at some canaries. We can use this same thing. So every function will not have a canary. And you've probably seen this in Linux. There's a rhyme and reason to whether it makes sense to add a stack canary or not. The rules aren't super complicated. The rules are there vulnerable pointers? Is there something that is like an array or a struct that's like larger than like 24 bytes that has pointers? But if I had just have something like this, this will not have a canary because there's not any complex structs, there's not any vulnerable pointers, it's not taking any input. There's not any way there for like a buffer overflow scenario to happen. Right? Here, there definitely is. So I think I recompiled it. The problem is I should probably call the function. All right, if we take a quick look now at call me 2, we now see something a little bit different here in our prologue, right? We now have, as somebody pointed out, security cookie, and this is getting moved into RAX. That's weird. Where does the cookie go in Linux? It goes on the stack. All right. Anyone want to tell me what it's doing? Let me read like 4 lines of assembly.
Source RSP. Xerix to RSP plus.
Okay.
It's putting it on the stack, just
What is it putting on the stack?
the cookie.
It's a cookie.
Not really. It's XOR of it's RX. It's putting the cookie XOR to what's at RSP, and then putting it on the stack. right?
One more time.
It's taking. It's taking the cookie, putting it into REX,
Take the cookie, goes in RAX.
XORing that with RSP,
All right. I take this cookie, I XOR with RSP,
and it puts it on the stack.
and the result gets written onto the stack as a canary.
What's
All right.
the XOR do?
What does the XOR do? Well, it XORs, man.
Yeah, no, but
Well, what is its purpose? So here in the debugger, we can just dump out our security cookie. Okay? It is just a random value. We don't have the same convenience that we have with Linux when it comes to fork. Right? Forking isn't a thing in Windows. You have create process. Right? You just create a process and it just exists. And so this is unique for everyone. We don't get that kind of fork brute force scenario here. So every time that you run, that will be randomized.
so it doesn't start with zeros.
Oh, somebody keenly observed that unlike on Linux, the stack canary, or at least the secret value, the security cookie, let's use the right terminology, does not begin with 0. So that does mean, and I don't know if that's worth writing a challenge. I challenge about.
You can like print it out if you have like a print.
Right. So unlike the Linux canary, which always ends in 0, or least significant byte is 0, which prevents you from writing something right up against it, right? Because you have that null byte. We don't have that scenario here in Windows, at least with just stuff. Let's see how far the debugger is going to take me. If I hit the letter T, it's really going to go for it. Yeah, that's fine. Boom. Okay. Oh, no, I didn't. I need to break on this function. Where am I? Call me 2. We'll break on call me 2. Now we go. Now we T. Now we're on the other side of call me 2. And if I were to look at this random value, display the quad word right there. Give me just the 1. And then I also print out that stack cookie. We see that those are different values because, as it was pointed out, this value that is written to the stack that's protecting the saved return address is the XORed result of the cookie in RSP. Now, is RSP going to be different at different points in execution?
Yes.
Yeah. So does that mean that if I were to leak out this value, that I could use it in another function? No. So that is what is different there with your stack cookie, your stack canary. And if you looked at the tail end where it gets checked before ret, it's just doing the opposite. It's grabbing the XOR value, XORing RSP out of it, and then comparing it against the secret cookie. Does this mean that Microsoft has a better canary?
It's a different.
Right. I don't know that it's better. It's different. It presents different problems. Like, what things, just thinking about what you've seen here, can you reason about? Because the one challenge I had plays with this idea.
XOR. Or
Well, the next 3 challenges I'm adding play around with the concept of the canary and what you can do with it. And I don't want to solve the fun things that I came up with here. Instead, I want you to start thinking about what happens if I could leak this. Or not, yeah. But I can't overflow this. My overflow is somewhere else. Does this canary tell me anything about the canary 5 functions later?
Yes, but we need more leaks. But I think
Then yes, but I need more leaks.
This is the XOR value, right? So
This is the XOR value, right? So what I have,
it can tell me what RSP was, since it's it's just the secret cookie XORed with RSP, right? And then if I find another canary somewhere else, that's another RSP XORed with the same secret cookie. So I can
That's
find
true.
the differential between them and find some information about that.
All right, you could learn some information there, right? It would be great if I had RSP, right?
Yeah.
I think the first one gives you RSP.
First challenge.
First challenge. It'll give you a RSP. Because if I can figure out RSP, and I don't need to know this literal RSP, but if I have anything that is a leak that is on the stack, I can track how the stack grows and shrinks from any leak to figure out what is the RSP that is being done here. I could have a leak 5 functions away. It's somewhere on the stack, even if it's just a local variable, right? Like imagine that I had let's make this. Give it some local variables. Is this sufficient?
Yeah,
It is.
we can calculate.
We can calculate, right? It's not super obvious what the delta between these two locations is from the C code, especially when you start thinking about that hex 20 shadow space, right? And the stack, when you call, needs to be 16 byte aligned. It will kind of function, and then eventually it'll just not. And I'm not entirely sure what the mechanism there is, but rule of thumb, the compiler will make sure everything is 16 byte aligned. And so if something is calling something, we could ballpark this. For instance, this is going to be 246 rounded up to whatever is 16 byte aligned, which is probably 256, plus hex 20. And so this is probably going to bring the stack frame down by 256 plus 32, 288. Is that right? Did I math?
Say about close.
What is close enough, right? And we can do that for each function that gets wrapped in. We know there's going to be at least the hex 20 for the shadow space since it's calling something. And then we have to account for the local variable, right? This long here is going to go at 8 bytes, but we have to be 16 byte aligned, which means this is really going to be 16 bytes on the stack, assuming the compiler is behaving reasonable, right? The compiler is going to do what it's going to do. If I were to, am I still on? Oh, that's going to fail. See if this thing builds. The elusive semicolon strikes again.
Still need to call back whether you want it, right?
Success? Success. Okay. And so now, if I were to look at Wrapper 1, we got hex 28. Was that what we thought? No, because I said it was going to be 16 byte aligned, right? So why am I wrong? I'm kind of wrong. It was 16 byte aligned at the call point, which pushes saved RBP. So to be 16, which means it's currently 8 byte aligned at this first spot. All right. So we have to subtract hex 28 to get 16 byte aligned, and this 8 bytes is what's right next to saved, or the saved return address. I think I said saved RBP, but the saved return address is from the call. Okay. We don't have any canary here because it's not vulnerable to, I know Flowy doesn't have some stack pointers that can get overridden, doesn't have large arrays, et cetera, et cetera. So that one's straightforward. Take a look at wrapper 2. All right. Yeah, same thing. Wrapper 3. And we could add all of these stack offsets that we see in the assembly to find the distance up the call stack and down the call stack from any leak that we have. Does that make sense to everyone? Good. All right. Last thing, I think, let's break on wrapper 3. Oh, it wants input, doesn't it? No, no input. There we go. Wrapper 3. And we look at the call stack here. This is a strange way to show a call stack. If I were to look at wrapper 1, it says the return address is F209. That return address is going to point to this function. And so we actually end up kind of reading this thing diagonally. Let's look at unassemble this address, limit 1. What did I do? 209. We see the return address at 209 is the return address for this function frame, but what it's returning to is the frame before. All right? RSP. Whose RSP is that?
Child. Colleague.
Well, instead of starting at the end here, let's look. We're in wrapper 3. Right? We're in wrapper. What is my RSP? Is my RSP on here? Okay. So this is my RSP, not my child's RSP. So if I wanted to find where in memory is this return address, where do I look? The saved return address, is that near my RSP? No, it's up near my caller's RSP. So if I want to find the return address for the frame 0, I actually want to look near the child stack pointer of frame 1. If this makes sense to you as a way of thinking about stack frames, please let me know how. I have a hard time justifying this in my my own dome here. And so if I examine, let's do 4. 4 quad words, hex 20 bytes behind my parents' or the caller's child stack pointer. It should show me where the region of memory where the saved return address is. I'm doing hex 20 specifically. This isn't a good function for it, but minus hex 20 is where the stack cookie will be, if there is. And so this is a good This would be where my stat cookie is. This is my return address. Right? Because the return address is just behind, because I did the child stack pointer minus hex 20. So the saved return address is just behind or in front of, depending on how you look at it, but right next to that child stack pointer of my parent. And if I were to restart this and break it at who has gets, call me 2. Does let's step just a little bit. Oh no, I went too far. That's okay. We're still in call me 2. If I look at the backtrace here, I'm in call me 2. I want to see where the canary is. Like, am I getting up to the canary with my buffer overflow that's hanging out inside of call me 2? What I want to look at is the parent's child stack pointer minus, I'll say like hex 40. And let's just let Microsoft decide with the right number quad words for me. What we'll see here is this is my saved return address. At this location, this is my XOR RSP cookie canary. And this is where I start seeing my A's, which we can throw in there if you want. Do you trust me that this is the canary, or you want me to XOR?
XOR.
XOR? All right. So I need to exert. Yeah, I'm thinking. I think it's X example underscore security. Yes. All right, so that's my cookie. We're going to take that, we're going to XOR the cookie with this value, which is what I'm claiming is the canary that's chilling on the stack. We get EE5DFF90. I'm currently in this function, so that means I can look at the register RSP, and we see these are, in fact, the same value. Any questions about the canary, thinking about the call stack, dumping stuff out? I got one trick that will probably save you a lot of pain because you will suffer here. If not in the existing challenges, definitely in the new ones. There is this cool memory tab. Okay? And I am, as you know, a devout follower of the terminal. But this memory thing is kind of cool. All right. So if we pin this thing right here, we see that we've managed to split our screen. Now, by default, it's going to follow whatever we type up here, and it's going to follow the instruction pointer. That's kind of useless, right? I really don't care about that. Let's imagine that, no, I got time? I got time. Let's do it. Let's write some Pwn tools. Oh, since the Windows changes the home directory, we can have a fresh do.py. It's a big day. So from Pwn import star, one thing to be aware of working with Pwn tools on Windows is Pwn tools on Windows is definitely in development. That means that you're going to run into things that do and do not work or things that misbehave. There is some useful functionality that applies to this module for sure. There's also functionality that you would expect to work that definitely does not. That doesn't mean you can't use it. It means you need to be a programmer and just implement something that does the same thing. Nice thing that works, process. What are we running? Example.exe. Nice thing that works. Well, nice thing that doesn't work. Receive until. Does not work. So what does this thing do? Does it?
You printed.
We don't print anything? Oh,
Oh, your own.
yep. People are getting on the dojo. Let's print something back up in main. Put my secret value is some secret value. Okay. So now my amazing binary says total and some secret value. As somebody who is a devout follower of phone tools, you might be tempted to do something like this. You think it's slow?
It's either hanging or snow.
Something not good's happening, all right? The question is it Python or is it the dojo? Do we just curse the computer? I propose that I hit Control C and we look at what's failing here inside Pwn tools, which I'm sure can be fixed, right? Like I said, this is dev, is that it is failing to properly pull this in timeout, right? And so this will just hang. Similarly, receive all will not work. I'm going to try and show you like one way to implement this because this shouldn't be that hard. Anyone have any ideas on what you might want to do? How would you do it? And I'll show you my way, and then there's probably one that's 10 times better that I get to learn. Any takers?
But why? Like, why does it not?
Okay. So the question, why does it not work? Question was, is it buffering? So it could be buffering, and buffering will be a problem.
Does receive line?
Does receive line work? That one's kind of surprising.
So there goes my solution.
I was a believer in receive line.
But receive works, right?
Something works.
Right?
All right, wait a minute here. I was playing this game last night. Last night, receive line worked. Well, we did forget some boilerplate, didn't we? What's our boilerplate? Okay, so your contact arch. Still no allowed. Oh, well, I'm only receiving a byte.
Try receive one. I don't know what this p.receive itself did.
It's
I was a believer in receive line. I really was. I wonder what I got going on here. No, I don't have anything frozen there. Component per star. AMD 64 is good. Windows good. P equals process. We're good there.
Does example exe actually print anything?
It does.
That's same. Okay, that's
Does this work? I swear receive line works.
not works.
Oh. What? And then we do call me to for this gets. Which should append a new line. Oh, is that what I want to do? When I change the code, I have to rebuild the binary? What did I break? Oh, something has it. Who has it? The debugger doesn't have it. Oh, I did have it. This was all cursed.
Still cursed.
So we see that the I/O and buffering is definitely getting to us here, right? Or is it? Hmm. So it wants to be played with. Gotta give it something. Let it know you're there. Right? Go out there and give it a little touch.
Use a p.set.
Maybe we do one of these.
p.send line.
All right. Oh, I don't have the answers to all of the mystery, but be aware that like this will happen. It is going to be something you're going to have to kind of play around with. My suggestion to emulate something like p receive until is to create a generator. Familiar with Python generators? Python generators are like made up lists. They're functions that generate objects. So you just define a like my generator. My generator is going to take a p, and then we say while. And let's do while p dot poll is none. What does p dot poll return? It returns none if the process is still running, right? And it returns an exit code if it has returned. So if it returns none, then this process has something. We're going to yield. This is what makes it a generator instead of a function. We yield some value. In this case, I'm going to go with p receive line.
What's yield?
Yield is I'm going to give something to you, but I'm not done yet. So generators are a little bit weird. I think if you see me use it here, it'll make a little bit more sense. So I'm going to say, let's call this receive all. This is because that's essentially what I'm emulating instead of my generator. It just happens to be a generator. We can say for line in receive all p print line.
When would receive all stop?
What's that?
When would receive all stop?
So when we run out of stuff, this is no longer true, right? Because poll is going to not be none. Poll will be some exit code. Do you agree?
Yes.
So when I run out of stuff, whenever Pete poll returns a valid value, receive all will leave this infinite loop, and our function returns implicitly. Right? Because I've reached the end of the scope. I've left the while loop. I then leave this function call. And so what happens here is this is creating something that's called a generator, which is a function that you can iterate through to dynamically pull the values. Every L is going to be a yielded line from this process.
But those lines only they only exist after receive all finishes.
No.
As it's going.
Yield happens every time that it is iterated upon. So I could, this is some Python shenanigans here, but this like 4L in something, the act of iterating, is really calling next on thing, right? In this case, my thing is a receive all P. So I could say my generator is receive all P because I need an actual instance of this generator. And I could say print next gen, print next gen. This, assuming that I write reasonable Python, should give me apparently,
Those get signed in interact.
where am I? Python do def receive all P process. Oh, I got to give it the touch. Print next gen. Oh, some Python guru is going to get me here. Next gen did the. Oh no, that is what happened. That was good. Okay, so it only had one line in this case because we pulled out before I read the value. But to your answer of how does this thing stop? This is the stop case. When you iterate through any iterable in Python, you don't know how long it is. You just like keep going on this list until something deeper, as you're just like happily marching, says, "Hey man, stop iterating." Right?
But wasn't there a line after total this?
Now, this is because of my poll being lame. So I lost a race here because you could envision the scenario where this process exits and this is not none before I read from the pipe.
Directly line crashes.
How? So you yield, and then it would be.
I could do this and I should get all of them.
Like stopped.
I did get all of them. And then there's my first line, there's my second line, right? So the reason that I lost what I had P pulled here is because the check isn't do I run out of, right?
You just do it.
Right. Do I have an exit code? And so that was not a good terminal state. Where here I just say, let's go for it. I'm surprised that ended up as happy as it did, but it did. Right. And so generators are weird generative lists. That's why they're called generators, right? This function creates an instance of something that can be iterated on. Every iteration is a call into this function, and the value that is returned is whatever is yielded. Execution continues from this yield next time it's called.
So that gen equal receive all line is not actually you are not running the receive all function yet. That's just an like
It's an
like an
instantiation,
object.
yeah.
Yeah, that you can like keep calling next on or like a for loop on, and every time it's gonna do one yield.
Yeah.
While that while true is going. Okay.
Yeah, so this did work, but what you typically do is like for L in gen print L, right? Because this is an iterator, so why call next a whole bunch of
So
times?
every time that for loop runs, it will call that receive all once.
Yep.
Okay.
Which is why I'm getting those same values there. Okay. And alternative data streams.
Oh, sounds like ads.
Yeah, the advertising.
What?
And what do we see there? We get the same result where now it's printing that, then it's yielding the next one, then it's yielding the next one, right? And so what happens there, despite my Python socket blowing up, which I could try catch, do whatever to handle that. The way generators work is every yield is I'm going to return a value, and then next time that the function is called, it continues from that point to yield the next thing, continues to yield the next thing. But the typical use of it is to not do multiple yields.
So why do you need the while true?
So if you don't have the while true,
It would exit.
it would exit and you would get stop iteration.
So why isn't it always while true? Why would we need another like exit condition?
So while true is not the ideal
Exit.
scenario here, right? The terminal state could be p.poll. The terminal state could be that you hold, for instance, right? Like you could do something like this. This would be valid. Here, when I initially start, I'm getting the first line, I'm yielding it, and the next time that it's called, I'm going to get the line. And if it is a valid line, right, it's not empty, not a falsy value, then we continue the iteration and loop it. If it's a falsy value, then when we loop back around for this check, that would be false. This would then return stop iteration because we would exit that. Right. Generators are cool. Python is cool. Some of it is just pure magic. This is one type of Python functionality that I used to think was pure magic, but every once in a while there is a good use case for it. Right. Additionally, you could turn this into a comprehension, right? L for L in gen, and now I just have a list, right? I used a generator to generate them. I used a comprehension to turn this into a list of all of these. And so anything that Pwn Tools does that misbehaves or acts a little funny or has some type of weird nuance to it, like, hey, I have to pass something before I get some IO, you can work around. Any of the challenges that deal with a lot more of this type of stuff, I am automating it in Python. I am verifying that it can be done from the Windows side. So I've implemented something that does the same thing and it wasn't too crazy. But just know that there will be some weirdness there, right? If you want to be like super ambitious, go check out the Pwn Tool source code, submit a PR, right? That would be awesome. Okay. But let's see if we can get to this canary. That is what our original goal was, right? What function am I in? Call me to. I'll show why this memory thing is useful. How big is my buffer overflow? Airtaggers? Come to touch home?
Is it hex 118?
Is it hex 118? It's a pretty good number. And so you got that from here
Yeah,
to here. Well, let's give 118 a try. Let's do 117 because of the send line.
oh, hex.
No, you want hex. And we're going to use our good friend. It's not GDB, but I wish it was. All right, we've seen this trick before. All right, we've got our breakpoint. We set it free over here. We set it free over here. Bad stuff happened. Hmm.
Less than 6.
Did I set the breakpoint at the wrong spot? Unassemble, call me too. F-150. Windy Bug just said no. Unless I missed. We have call me, which doesn't do anything interesting. We have puts. We have call me too. Well, let's do 256. Let's see if that. No, let's just fill the buffer. Let's see if we can find it in the old memory view here. GDB me. Okay, we have no breakpoints. I want to go to the first thread and then set a breakpoint at call me 2. That seems like a reasonable place. We go free. Go free over here. You are not happy. Why? Oh, I sent 256. A good old new line, man. First thread, breakpoint. You go free. You go free. This breakpoint is not very happy. But why is this breakpoint? I'm going to remove PDB. I'm going to remove the executable. We're going. That's okay. Come on, Vim. We're saved by the Vim buffer. Remove the executable. Okay. I think what was happening there was it was falling out of sync. The PDB wasn't for the exe. Okay. I want to break example That exists. It's there. You're free. This is why live demos are fun. Oh, I'm a goober. What am I doing? Okay, I do this. What is the binary doing? It's running, right? What's the binary doing? We get process. What is this thing? Example. It's there. It's chilling. It's alive. What is it doing? This is my own lack of sleep, but I do this. We go to thread 1. Where am I? Because I attached. I didn't start from the beginning. I'm inside read file. The binary is waiting for the input. I'm setting my breakpoint at the beginning
Oh, of something already.
of call me to, which I'm already past. As fun as it is to blame the tools, right? Sometimes you have to admit the problem may be you.
Maybe you should put the input before you start the process. No.
I can't do that
Yeah,
though,
I can't.
right? This is okay. I can still get what I want. What do I want to see?
Stack.
I want to see the A's in the stack. You have any idea where the A's in the stack are?
Oh, break somewhere else. Column 2.
You want me to? Okay. So we could set a breakpoint further up in call me to. Right? We could set a breakpoint after the call to gets. That'd be pretty swell. The other thing I can do is I can look at this address if I wanted to, right? Now I could set the breakpoint, but you can just go up like Finney. It's GU, go up. But this one I like. I like goo. Right? We can goo. All right, the debugger is my friend again. We can goo our way up. Now imagine if you had this call stack and none of this information.
So it's like without the P.
Yep. You will have none of it. And so which function you want or which frame you're interested in can become quite problematic. All right, I think we made it there. Now, how do I look at the canary, the area that I'm interested in? So I want to find, trying to overflow from my buffer to overwrite this return address. So where do I want to look in memory?
Check this thing.
I want to check the stack, right? And so we could do this old trick. We do the diagonal, display quad words, this guy, minus hex 40. I don't see anything. Minus hex 80. Okay, there they are, right? Now, I'm going to show you another way that we could have looked at this. For the record, we see that I'm just shy of, that's hex 40. This is, this should be my saved return address. You see that highlights. This is my canary. This one happens to end in 00. That's just by chance due to the XOR. And so we see that we were a little bit shy there, right? And we could do this, and honestly, I don't mind doing this because I'm a GDB guy. But we can do better. Sometimes the GUI people have figured something out. I must confess. All right, so I've attached. I'm back here. We're about to read. I need to set my thread to be the first one so I get the trace that I want. Here's call me. And what I'm trying to find is this saved return address, which we said was this minus 20 over here in our scope. Let's make him be that minus 20. We hit enter. This highlights right here. That is where my canary is. And if I were to, oh, goo, not K. We goo, not only will we see the values change, but we get pretty colors, right? Which honestly is quite nice. So the moment that they are changed, they're highlighted in red. So you can see what just happened between your previous step and your current step. And so that is a great visualization of, okay, here's where all my A's are. That's the location I'm interested in. Now I can kind of see what's going on. Questions, comments, concerns? Okay. ROP is still ROP. Return addresses still go burr. Any other questions? If not, we will probably call it there. I suppose I should probably show you how. Do I have... Where did I hide this? I moved it. Okay. That's something I'll have to fix. There's a Win RPI is kind of your ROP gadget tool on the Windows side. But apparently I made that go away for you right now. Works very similarly though. All right. The module is still very chill. I'm trying to make the later ones kind of interesting because the first, I don't know, 5 or 6 levels of this Windows module you can cruise through pretty quick. Next week, we will talk about some more hyper Windows specific stuff that just doesn't exist elsewhere. All right. With that, I'll leave you all. Goodbye. Good luck. Have fun. Good stuff.